Hello students, welcome back to this channel. Today we'll study a very important topic of chapter number 2, that is potential energy of system of charges. Okay, we have already studied about potential energy in our previous video lecture. Right? What is potential energy? Potential energy, the definition was work done in bringing a charge from infinity to a point in electric field. Right? That was potential energy. So the work done in bringing that charge from infinity to a point in electric field is stored in the form of potential energy. Okay, so the question can be asked either find out the potential energy for system of two charges or a system of three charges. Okay, so both are very similar. Let's take Q1, Q2, and Q3. Okay, these are three charges, and our aim is to find out the potential energy of the system of these three charges. Okay, so initially what we have to think that, let's think this is the space. Okay, and there are no such charges. So first our aim is to bring charge q1 from infinite to the point. Yes, so let's name this point as A, B, and C. So I'm bringing a charge from infinite to a plane to a point A, Q1. So what I need to do, I need to find out the work done in bringing charge from infinite to this point. Clear? That will be the potential energy. Now, for second charge, I am bringing charge Q2 from infinite to a point B here. Okay, so now that work done will be stored in the form of potential energy. So the total potential energy will be equal to U1 plus U2. Okay, now bringing a third charge from infinite to a point C. Clear? And this will be the work done in bringing the charge. So this will be stored in the form of potential energy. So now the total potential energy will be equal to work done in bringing charge Q1 plus work done in bringing charge Q2 plus work done in bringing charge Q3. Okay, clear? So let's start with this derivation. Okay, so at first we are imagining that there is no such point where there is any charge, means there are no charges present. But we have already started discussing that there are three charges. We have to find out the potential energy. So first, let's find out the potential energy or the work done bringing the charge Q1 from infinite to a point A. Let's select this point A. Okay, now at present, let's take this charge, this point A, B, and point C. Okay, so now there are no such charges. Okay, so now what is the potential at A? What is the potential at A? As there are no charges in, the potential at A is zero. VA is equal to 0. Clear? Now we had already studied the formula. Work done in bringing a charge from one point to another, that is equal to delta VQ, or I will write down VQ. Okay, so now what we are doing, we are bringing a positive charge Q1 or any charge Q1 from infinite to this point. Okay, I am bringing a charge Q1 at this point A. So work done in bringing a charge Q1 from infinity to A, W1 will be equal to potential at A into Q1. But what is potential at A? 0. So this will be equal to 0 into Q1. So this will be 0 joule. That's 0 joule. Okay. So work done in bringing a charge from infinite to a point A is 0 joule. Okay. Now what is the potential at B? Now we want to bring a charge Q2 from infinite to a point B. What is the potential at B? Potential at B. Now see, Q1 charge is already there. Let's take this position or this distance as R1. So now what will be the potential at B? K Q1 upon R1, right? Potential due to a point charge, KQ by R. So the potential due to charge Q1 at B will be KQ by R1. Clear? Okay, or let's take this as R12. Okay, this is position 1, 2, and 3. So it will be KQ1 upon R12. Clear? Now, work done in bringing a charge Q2 from infinity to B. So there will be W2. This will be equal to potential at B into charge Q2. Now what is potential at B? K Q1 by R12. So this will be K Q1 by R12 into Q2. Okay, so this will be KQ1 Q2 upon R12. Okay, so if I only want to find out the potential energy of system of two charges, I'm noting it down extra. Potential energy of system of two charges means Q1 and Q2. This will be equal to W1 plus W2, right? Okay, work done in bringing a charge from infinity to Q1, sorry, to A and bringing a charge Q2 from infinity to point B. Now, this work done is stored in the form of potential energy. So, W1 is 0 plus KQ1 Q2 by KQ1 Q2 upon R12. Okay, so if the question is asked only for system of two charges, then you have to end it here. Okay, clear? Now, some important points. See, if first I am bringing the charge Q2 from infinity to B, and then I am bringing charge Q1 from infinity to A, then also the formula will remain same, right? So either bringing charge Q1 first or charge Q2, the potential energy of system of two charges, I just forgot, I had put here Q2, right? Or let me write it down here. Okay, the system of these two charges, the potential energy will be K Q1 Q2 upon R12, right? If Q1 and Q2 is greater than 0, right? Means either both are positive charge, then it will be positive, or both are negative charge. Okay, in this case, the potential energy will be positive. Reason, in this case, both will be like charges. So there will be repulsion. So positive amount of work must be done to bring them together. Right? But if Q1 and Q2 is less than 0, that means either one of them is positive and another of them is negative. So what will happen in this case? There will be attraction. So negative amount of work must be done So in that case, the potential energy will be equal to negative. Okay, I'm just writing here symbol. I just forgot to write down symbol. U will be equal to W1 plus W2 K Q1 Q2 by R1 2. And these are some important points that you have to note it down. Okay, first this, second. And remember one more. Either you are bringing charge Q1 first or charge Q2. In both the case, the formula remains same. Okay, so first you can just go through this derivation. Then we'll move for third charge. Okay, so now let's see for third charge. And also one more thing, you can see here, it's KQ1 Q2 by R12 means the potential energy directly proportional to product of the charges and inversely proportional to distance between them. This is also one important point. Okay, so you can just note it down. Now let's move. Suppose the question is asked for potential energy of a system of three charges. Okay, so let's name this as one, this two. And now let's move forward. Now I want to bring another charge Q3 from infinity to this point C. Okay, let this be the position R13 and this will be the position R23. Okay, so now what is potential at C? That will be equal to Vc, and this will be equal to potential at C will be potential due to charge Q1 plus potential due to charge Q2. So due to charge Q1, K Q1 upon R13, and due to charge Q2, K Q2 upon R23. This is the potential at point C. Okay, so now I am bringing a charge Q3 from infinity to a point C. So now work done in bringing a charge Q3 from infinity to C, W3 will be equal to again VQ. That means VC into charges Q3. So what is VC? KQ1 by R13 plus KQ2 by R23 into Q3. So W3 will be equal to KQ1 Q2 by R13 plus sorry, not Q2, Q3, KQ2 Q3 upon R23. This is the work done to bring a third charge Q3 from infinity to a point C. So now the total work done is stored in the form of potential energy. Therefore, total potential energy will be equal to W1 plus W2 plus W3. So 0 plus K Q1 Q2 upon R12 plus K Q1 Q3 upon R13 plus K Q2 Q3 upon R23. That implies, or I can write it down, of system of three charges. So U will be equal to KQ1 Q2 upon R12 KQ2 Q3 upon R23 plus Q1 Q3 upon R13 plus KQ2 Q3 upon R23. What I did, I added W1 0 plus KQ1 Q2 by R12 and this. So this is the total potential energy of system of three charges. Okay. So what we have to do? First, consider that there are 3 points A, B, C. Work done in bringing a charge Q1 from infinity to A, W1. So for that, find out potential at VA, and the W1 will be VA into Q1. Then at point B, potential at B, okay, plus bringing a charge from infinity to Q2, so VB into Q2. And here VC into Q3, and add all the three work done. This will be stored in the form of potential energy. Clear? This is a very important topic. It can be asked in 4 marks. Okay, so just note down this derivation of potential energy of system of charges. Okay, now let's move to the next topic. Next is potential energy of system of two charges in an electric field. See, that means now an external field already exists. So let's say that this is an external electric field existing. Now there are 2 point A. Let's take that position of A is R1 and point B having position R2. Okay. Now I have to bring charge Q1 at point A and Q2 at point B. Okay. So that will be that work done will be stored in the form of potential energy. Okay. In previous case, there was no external field. So work done in bringing charge Q1 plus work done in bringing charge Q2 plus work done in bringing charge Q3. Okay. Similarly, only we will solve this one. But the only change is here already an electric field exists. That means there is some potential at A, external potential, okay, at A, and also external potential at B. The potential at A, let's take it at V of R1, and the potential at B, V of R2. Initially, when there is no charge, as there is external field, so there might be some potential. So let's take that potential at A, V at R1, and potential at B, V at R2. It's not V into R1, potential at a point, position R1. Okay. Now, let's bring a charge Q1 from infinity to this point A. Okay. So work done, or let me write down potential at A and potential at B, V of R. Okay. Now work done in bringing a charge from infinity to A. So W will be equal to VQ, means V of R1 into Q. So Q into V of R1. Okay, let's name it as W1. In the previous case, as there was no electric field or no existing field, so the work done in bringing the first charge Q1 was equal to 0. But here there exists a field. Okay. Now let's bring a charge Q2 from infinity to the point B. Okay. Work done in bringing a charge from infinity to B. So now there will be two work done. First, work done against this field, existing field. And second, work done against the field due to Q1. See now, when there is no charge, sorry, it's Q2. When there is no charge, there are two fields. One, this existing field, and second, the field due to charge Q1. And now we are bringing charge Q2. So this will be equal to W2 work done due to existing field Q2 into V of R2 and work done due to against the field due to charge Q1 that will be equal to Q2 and what is the potential at B due to A. Okay, what is the see initially it was V of R2, but now there is one more potential due to charge Q1. And what is the potential to point charge? K Q1 by let this be R12, then that will be K Q1 upon R12, right? Okay, or else let me write down Q into potential due to A. So Q2 potential due to A will be K Q1 by R12. Clear? So now the total potential energy will be equal to W1 plus W2 plus W3. That means U equal to W1 Q into V of R1. Potential at position R1 due to existing field plus Q2 into V of R2. Potential at position R2 due to existing field plus KQ1 Q2 by R12. You can also put instead of K 1 by 4 by epsilon 0. So this is the potential energy of a system of two charges in existing field. Okay, so just note down this derivation. Let's move to the next topic. Next is potential energy of a dipole in an external field. Okay, so now we will find out the formula for potential energy of a dipole in an external field. So see, as you can see in figure, electric field is in this direction. And this is a dipole, minus Q plus Q. So dipole moment direction from negative to positive. So the angle between E and P is theta. The distance with the positive and negative charge is 2a. Okay, so according to the formula, the dipole moment P is equal to 2aq. Okay, dipole moment P equal to 2aq, right? When angle theta is angle between P and E. Clear? So what will happen? Positive charge will experience force in this direction, negative in this direction. So a torque acts on it. Therefore, torque acting on it. So what is the formula for torque acting on a dipole in a uniform electric field? Tau equal to P E sine theta. In vector form, it's P cross E, right? So it's P E sine theta. Okay, this is the torque acting on it. Now, if I rotate, let's say this is the position of dipole. If I rotate in this way, okay, as soon as I will release it, it will try to be in this original place. Means here there is positive, here there is negative. Positive charge experiencing force in this way, negative in this way. So I rotate in this way, positive will in this way, negative in this way. So we try to align in zero angle. Okay, clear? So now let's say that dipole is rotated from theta 0 to theta 1. Okay, or let's say from theta 0 to theta. Any angle from theta 0 to theta. Dipole is rotated from this much angle. So we need to do the work to rotate the dipole from theta to theta. So the work done will be equal to tau theta. Integration of theta 0 to theta tau d theta. Clear, small amount of angular displacement in torque. Just imagine in linear motion, W equal to F into D, force into displacement. So here torque into angular displacement. Now what is torque? That is equal to PE sine theta. P is constant, E is constant. So integration of sine theta, it will be minus cos theta. Integration of sine theta is minus cos theta. Theta 0 to theta. Clear? So this will be equal to PE. First I will put theta minus cos theta minus cos theta 0 will be plus cos theta 0. Clear? If I consider theta 0 equal to pi by 2, then cos pi by 2 0. In that case, the work done that will be equal to minus Pe cos theta. That means the work done is stored in the form of potential energy minus Pe cos theta, or in vector from as it is cos, I will write down P dot E minus P dot E. Okay, this is the formula for potential energy of a dipole in an external field. Okay, so now if theta is equal to 0, potential energy equal to minus PE, and that is minimum. Okay, because if this is positive, this is negative, angle is 0. It is the most stable position. Positive charge acquire force in this direction, negative in this direction. Okay, theta equal to pi by 2. At that time, u will be equal to 0 because cos 0 is cos pi by 2 is 0. And if theta is equal to pi, that is 180, u equal to minus cos 180 is minus 1. So it is PE, that is maximum, because it's just opposite. It's in this direction. This is positive, this is negative. Positive charge will experience force in that direction, and negative in this direction. So this is the most unstable position. Okay? So this was about potential energy of a dipole in an external field. Just note down this topic. Okay, so that was about potential energy of a dipole. I'm repeating in short what we did. We took a dipole, placed it in external electric field. The angle between electric field and dipole moment is theta, right? So in this situation, the torque acting will be equal to Pe sine theta. Now, when we rotate a dipole from angle theta 0 to theta, work is done and that work is stored in the form of potential energy. So, we'll find out the work done, that is tau d theta. Okay, because we are taking a very small displacement and integrating it from theta 0 to theta, putting the value of tau, Pe sine theta, integration of sine theta is minus cos theta. Okay, so we get this. Finally, considering theta 2 as pi by 2, in this position, man energy is 0, the work done equal to minus Pe cos theta. So this is stored in the form of potential energy, U equal to minus Pe cos theta, or minus P dot E. And then there are three cases. Case is 1, when theta equal to 0, it's minimum energy. When theta equal to pi by 2, energy is 0. And when theta equal to pi or 180 degree, the energy is maximum. Clear? So that was about potential energy of a dipole in an external field. Okay? So students, that's it for today. Thank you.